The year is 2100. The Earth's once flourishing ice caps have melted. Once great cities including Alexandria and Shanghai are now claimed by the ocean, destroying millions of people's homes and livelihoods. Crippling natural disasters are now a norm, and life on Earth is in many places a constant battle for survival. This may be slightly extreme, but it paints a picture as to how close humanity may be to a mass extinction event. After all, extinction events have been very common over the Earth's relatively short lifespan. There have been 5 definite mass extinction events known to us at this current time, and it is believed that our current situation could be a 6th. However, even if we are not to be wiped out of existence by global warming, there are many other events that could be sprung upon us that could threaten humanity as we know it. A similar disaster as to what happened to the dinosaurs at the end of the Cretaceous period could occur, where a large asteroid impacted Earth and an estimated 75% of species were wiped out. A disease outbreak could also threaten humanity if we did not contain it in enough time, wiping out large quantities of the world's population. There is a large variety of causes that could soon be upon us that could threaten our existence here on Earth. I am still being very hypothetical, and events like these are largely improbable. However, humanity is largely unprepared if our home planet were to become uninhabitable. Currently, humanity is only beginning to look to colonize other planets within our solar system, with the most probable target being Mars. However, Mars is a very limited prospect as a potential second Earth as it lacks many similarities to Earth and is largely hostile to human life. It would also take a great deal of effort to terraform Mars, if it is indeed even possible. If humanity were to have a backup plan, it would be wise to look outside of our own star system and at planets more similar to Earth, making the challenge of creating a livable environment much easier. This brings me to the topic of this video. If humanity were to look at interstellar travel, would it be achievable with today's technology? And if not, how far away are we from achieving such a feat? When space travel is mentioned, the first thing that comes to mind is a rocket. It has been the bread and butter of space travel since its beginning, and continues to be used as the main method of propulsion in space missions till this day. This popularity may suggest that they are complex machines that have solved all the problems associated with getting spacecraft into space. However, rockets are relatively simple when compared to many other methods of propulsion on this list. Simplified, a rocket burns fuel, which turns it into hot gas, which is then propelled out the back of the rocket, which in turn propels the rocket forward. It's not exactly rocket science. However, rocket fuel is very heavy, and this is where we encounter our first problem. An interstellar mission would have to support human life for a substantial period of time, and to do this, a substantial and heavy load containing the supplies necessary is required. It would require a considerable amount of fuel to propel this load outside of Earth's orbit and outside of our solar system. This fuel also adds weight, and therefore more fuel is required, and so on. This problem is solvable, however the amount of fuel needed would be expensive, and many weight-saving methods would need to be employed in the spacecraft, once more encountering large costs. Another major problem with rockets is that they are very slow in terms of interstellar travel. The only interstellar crafts to be launched by humanity, Voyager 1 and 2, were launched by the means of a rocket. These crafts have only reached interstellar space in recent years, and were launched in 1977, and have been travelling at over 35,000 miles per hour. And yet, this is a minuscule part of the journey. If these craft were to travel to our nearest star system, Alpha Centauri, which is 4 light years away, it would take over 70,000 years more, and that's without slowing down at the other end. This brings me to my next point, the weight calculation. If we were to launch a rocket today, and it were to take over 70,000 years to reach the nearest star system, would it be worth it if in 100 years we launched a spacecraft that could travel considerably faster and reach its destination before the original craft? It seems that a rocket has too many problems associated with it if it were to be used for interstellar travel. Many of these problems would be solvable, however it would take time, money, and a considerable effort to solve them. Even if these problems were solved, using a rocket as a method of propulsion would seem illogical due to the weight calculation. Thus I could say we could confidently cross this off of our list. Another current technology that could be explored to send us to other star systems would be a nuclear type of propulsion. Not fusion but fission. Not controlled fission but uncontrolled fission. In simpler terms, nuclear bombs. Nuclear fission occurs when a neutron is fired at a large and unstable nucleus of an atom. The atom used in fission is commonly uranium. This nucleus then splits into two smaller nuclei, releasing a great amount of energy as well as three further neutrons. These neutrons then go on to collide with other heavy atoms, and the chain reaction continues. Nuclear bombs allow this process to continue until there are no reactants left to continue the reaction, resulting in a huge amount of energy being released. Nuclear power plants use this process as well. However, the reaction is controlled through various means including the use of boron rods, which absorb some of the neutrons, preventing them from hitting more nuclei. The use of nuclear bombs sounds like a novelty. However, there was a real prospect of a spacecraft powered by nuclear explosions being created in the 1960s. Whilst NASA was preparing the moon landing, the US government were funding them a further $10.5 million to research this prospect. It went so far, in fact, that many of the greatest minds behind the Manhattan Project that originally invented the atomic bomb were placed on the team behind the idea, with other famous scientists including Freeman Dyson being involved. However, this may be the only positive. The interplanetary type of the Orion craft planned to carry 800 nuclear bombs, weighing over 10,000 tons. This would be for a mission only within their own star system, so getting to another star system would require multitudes more of these bombs, further adding to the weight, which then requires more bombs to propel, and all of a sudden we end up in a similar predicament to the rocket equation. As such a large magnitude of bombs would need to be utilised, there will be masses of radioactive material stored near the living quarters of the spacecraft. This puts the crew of the spacecraft at a large risk of radiation poisoning, or risks them developing cancer. To combat this, large amounts of heavy material that have the capabilities of blocking out this radiation would need to be placed around the living quarters. This would further add on to the weight already in this very heavy spacecraft. Another very large issue with using nuclear bombs as a method of propulsion is slowing down. This is because to slow down, the same propulsion used to accelerate the craft must be used in the opposite direction. This means releasing nuclear bombs just ahead of the spacecraft to slow it down, and then travelling through the blast as you continue on your course. I think it's fair to say that there's a fair few problems with this. As the craft launches nuclear bombs to propel itself, it would have to launch nuclear bombs towards the Earth to lift off. This would render a large portion of the surrounding area unlivable, and the craft would also have to endure being the epicenter of a nuclear explosion. It's not only the local area that would be affected. Launching several nuclear bombs to escape the Earth's atmosphere would cause large nuclear fallout. Freeman Dyson explored the risk of a nuclear fallout with such a craft, and predicted that it would release the same amount of radioactive material as a 10 megaton nuclear blast. There are not only physical problems attributed to this idea, there are also legal concerns too. The Nuclear Test Ban Treaty signed in 1963 prohibited the detonation of nuclear bombs in space. This could potentially be another tripping hazard to the use of such a spacecraft. It is quite clear that using nuclear bombs to travel to other star systems was a ludicrous idea from the start, and will remain ludicrous. However, it could definitely be an idea that could be explored if it was humanity's last hope at survival. By that point, nuclear fallout and law would probably not be of concern anymore, and therefore it could possibly be explored. Another nuclear type of propulsion that could potentially take humanity to other star systems is nuclear fusion. Fusion is the opposite of fission. Instead of splitting atoms to create energy, fusion fuses two atoms together, creating a much larger energy than fission. Nuclear fusion has been elusive for many years. It has been seen as a future energy source for the world for a very large period of time due to its sustainability. It was first achieved in the 70s. However, despite 50 years of progress since, sustainable fusion still has not been achieved. Every attempt at nuclear fusion has resulted in a net loss of energy, meaning it produces less energy than it used to create the fusion reaction. A successful fusion reactor, however, could be soon in the horizon. A project funded and supported by many major powers across the planet, including the US, Russia, the EU and China, is currently being constructed in France. This will be a full-fledged nuclear fusion reactor and aims to act as a key power source for the people living around it. It is due to begin testing and first operations around 2025, with a sight to achieve first fusion by around 2035. The type of fusion hoping to be achieved in this reactor is deuterium-tritium fusion. Deuterium is a hydrogen isotope, which contains one proton and one neutron, while tritium is a radioactive isotope of hydrogen, which contains one proton and two neutrons. These two isotopes can fuse together if certain conditions are met. To give perspective of these conditions, we can look at our own star, the Sun. Fusion is also the process that fuels our Sun. This reaction is similar to the one hoping to be achieved in the reactor in France, as it also uses hydrogen fusion. For fusion to be obtained, it sustains a temperature of around 50 million Kelvin and the pressure that the immense gravity of the Sun creates. This emphasizes the immense challenge behind creating this fusion reactor, as we cannot recreate these pressures created on the Sun on the Earth, and therefore we must compensate with a higher temperature, a temperature of over 6 times higher than the Sun's core. When hydrogen is heated to these temperatures, it turns into high-energy plasma, which would instantly vaporize anything it touches. It therefore must be suspended from any matter on the outside of the reactor. To do this, superconducting magnets are employed. This keeps the highly charged plasma rotating in a ring around the reactor. These magnets are also the force that squeezes the hydrogen isotopes together for them to fuse, just as the Sun's gravity does. It is therefore known that fusion can be created on Earth, and with a bit of advancement, sustainable fusion can be created. This could have large potential when looking at interstellar travel. Firstly, if we were to convert the energy created by fusion into electrical energy, it could be used to power propulsion methods including ion thrusters. Ion thrusters contain a reaction that ionizes neutral gases and then propels these ions out of the thruster using magnets. These drives are incredibly efficient, being able to sustain prolonged acceleration of speeds up to 90,000 meters per second. However, they would be very impractical for an interstellar mission carrying a substantial load. This is because, although being very efficient, they create extremely little thrust. Current ion thrusters only generate a thrust force of around 0.5 newtons. That's the equivalent of holding 0.05 kilograms in your hand. This makes them only effective for light spacecraft within the vacuum of space. Today, they are only used for satellites and other small craft outside of the Earth's atmosphere. Thus, this method would be very impractical for carrying a fusion reactor, as the one currently being built in France weighs around 3,850 tons. Secondly, the beam of fused particles created within the fusion reactor could be directed out of the spacecraft using the same magnets that contain it, creating a thrust force. It is predicted that using this method, an exhaust velocity of around 25 million meters per second could be achieved. This is around 10% the speed of light. There is very little data on this prospect, and it is mostly just theory for now. However, it is clear that using these early calculations, that this prospect is indeed promising, and could be definitely looked at as a method of getting us to other star systems. Therefore, many obstacles still need to be overcome with fusion. However, it seems sustainable fusion could indeed be achieved in the coming decades. From then on, it is a real possibility that fusion could be integrated into space travel. Another method that could be used to propel us to other star systems is the use of antimatter. Antimatter is often associated with science fiction. However, it is very much a real thing. Antimatter is exactly the same as normal matter. However, every particle of antimatter has an exact opposite charge. For example, an electron's antimatter counterpart, a positron, has exactly the same mass, but the opposite charge. Despite these similarities, matter and antimatter do not mix. If a particle of matter and a particle of antimatter were to meet, they would react violently, annihilating each other and leaving behind only energy which is emitted as radiation. Although the properties of antimatter are relatively well understood, it is still a mystery as to how it exists in our universe. The Big Bang at the beginning of the universe should have produced equal amounts of matter and antimatter. These particles therefore should have annihilated each other as they existed in such a close proximity, leaving nothing behind, and yet we are left with an expansive universe of normal matter. This is still a mystery to this day as to how such an end product was feasible from the theory of the Big Bang. This is one of the scientific mysteries that the Large Hadron Collider was created to investigate into. The Large Hadron Collider is a particle accelerator which collides atoms at extremely high speeds. These collisions can create antimatter. These particles of antimatter can then be funneled off to study. This is one of the only ways humanity can obtain antimatter today, due to its absence in nature. The issue is, creating antimatter this way is costly and inefficient. Creating a single gram of antimatter using this method would cost over $100 trillion and would take a considerable amount of time. Very little amounts of antimatter have been produced to this date. However, this problem could be solved creating a factory specifically designed for the purpose of creating antimatter. It has been predicted by the US Air Force, who conducted a study in the matter, that if a factory designed for nothing but the production of antiprotons was created, the cost of creating 1 milligram of antimatter could be forced down to $10 million. If this was indeed true, it would make obtaining antimatter a lot more achievable in abundance. If such a powerful substance were to be readily available, it could be a very attractive prospect for use as a fuel for an interstellar space mission. A single gram of antimatter could produce the boost that 120 tons of conventional rocket fuel could. Antimatter-matter reactions are also even more powerful than the marvel of fusion, creating almost 300 times the energy that a fusion reaction creates. This is due to the efficiency of the antimatter-matter reactions. As both particles are completely annihilated, 100% of the mass of the particles is converted into energy. This is much more efficient than any other reaction including fusion, fission, and combustion. Despite the fact that we could possibly be able to create large enough amounts of antimatter to create a spacecraft powered by the substance, there is still the issue of storing it. As antimatter annihilates any normal matter it touches, it cannot be contained in an ordinary way. The current record for storing antimatter is an extraordinary total of 17 minutes by CERN. Thus, this limits its use as a propellant, as an interstellar space mission would certainly need to have fuel for longer than this short period of time. However, scientists at Penn State University have theorized how they could create a spacecraft powered by antimatter. The antimatter would be stored through the use of a ring of magnets. This will keep the antimatter in constant movement around the ring and away from normal matter, preventing it from reacting. These particles will then be transported once more using magnets to where they will be reacted with ordinary matter. The energy created through this reaction will then be transported using a long magnetic nozzle through a thruster, creating a propelling force. Therefore, if we were to solve the issues of affordable creation of antimatter and the storage of the substance, we could have a very efficient way of getting to another star system. However, these challenges are much larger than the challenges associated with achieving fusion, with current progress in the creation and storage of antimatter being rather primitive when compared to our progress with fusion and other methods. Thus, this could be a very viable method in the future. However, it is a very unlikely technology to be used in the coming decades. If humanity were to have the need to reach interstellar space with current technology, conventional rockets would almost certainly be out of the equation. However, the thought of using such technology does give a good insight into how large the scale of such a mission would be and the many difficulties such a mission would encounter. Nuclear weapons could certainly be a prospect if the issue of interstellar travel was pressing. Perhaps humanity's existence on Earth was being seriously threatened. The idea is actually technically sound, apart from the obvious issue of stopping and launching. However, research done into these areas could create a solution for them. Fusion represents a good possibility for interstellar travel. It creates immense amounts of energy from relatively inexpensive and abundant materials. Once efficient fusion has been achieved, which is likely in the coming years with the development in France, the technology could be easily implemented into a spacecraft and could propel a spacecraft to interstellar speeds, making this method a real possibility in the next few decades. Antimatter is even more efficient than fusion, and if this technology was harnessed, it would almost certainly be capable of taking humanity to another star system. However, the challenges associated with such an endeavour still exist, and their solutions are certainly still very distant into the future. Overall, it is clear that interstellar travel is certainly possible in the near future. However, much research and many discoveries must be made until it is truly possible. Even though the use for interstellar travel is very far-fetched, most likely being an apocalyptic scenario, research into the field would certainly be beneficial on Earth. Further research into fusion could possibly achieve a new type of fusion, deuterium-deuterium fusion, which creates a larger amount of energy than deuterium-tritium fusion, which we explored in this video. Not only would this make fusion-powered plants more efficient, it would make them a lot safer and economical. Deuterium is naturally occurring in seawater, and is therefore abundant in Earth. The method also ditches the use for tritium, therefore making it completely non-radioactive. If antimatter were to become economical to produce, it could also possibly be used to power homes in the future. Research into these fields would also create more jobs. SpaceX's advances into space travel have created thousands of new jobs in the recent decade. If governments were to launch funding into these methods for interstellar travel, it could create jobs on an even larger scale. Thus, interstellar space travel not only has the ability to potentially save humanity from an apocalypse, it could also have great implications on the growth of humanity on Earth and the efficiency of our species. This video was created as part of my Scottish Science Baccalaureate. For this, I must gather the opinion of my audience. Therefore, it would be much appreciated if you could complete the YouTube poll on this video. Thank you for watching.